don't want to do that. Okay, today we are looking at properties of exponents and logarithms. My hope is that everything we're going to see today is a review of Math 3. So we're going to go through all of the laws that govern exponents and logarithms. We'll do some examples together, and then you have some problems in Delta Math as a follow-up. And my recommendation is, if what we're doing today seems foreign or scary, spend some time with the Delta Math this weekend so that when I see you on Monday and we do some more practice, you will have specific questions in mind so that you know where you're stuck and where you're not. Yeah? Okay, so let's start with exponent rules. First one is the product rule. The product rule says that if I have an exponent with base a to the m, and I multiply it by another exponential with the same base, that I just add the exponents. And I hear an that means that sounds familiar. Yeah, so 2 to the third times 2 to the second would be what? 3 plus 2, which is 5. Good. Good. Product rule is just add. Very good. Next one is related. It is the quotient rule. So I have two exponentials with the same base, and I am dividing. What happens in that case? So multiplication went with addition. What do we think division goes with? Subtraction. Good. Those operations are related. And it's top minus bottom. So m minus n. Good. So for example, I had x to the third over x to the fifth. That becomes x to the top exponent minus bottom exponent, which is -2. Very good, x to the -2. Which brings us to our next rule. And our next rule is the negative exponent rule. So if I have a to a negative exponent, I'm going to write in red here, I'm allowed to take any expression and turn it into a fraction by putting it over what? 1. Good. I also know that when I've got a variable and I don't have a number out in front, the implied coefficient that I'm not writing is 1. There are ones hanging out that we didn't write because they divide out. I moved it up front for you. So the negative exponent, I'm going to leave the ones where they are, but I'm going to take the exponential and move it to the other side of the fraction bar, right, Sadie? So 1 over a to the positive m. When it moves to the other side of the fraction bar, the exponent changes sign. The 1 and the 1 are still there. Nothing else moved. I didn't need to write it here because I know 1 times anything is itself. I didn't flip the fraction. I just moved the thing with the negative exponent. That's important. Everything else in the fraction will stay where it was. And we have a perfect example. Our last problem gave us x to the negative 2 as an answer. You will never see a mathematician leave it like that. We don't like negative exponents. How would I rewrite that? Very good. Very good. 1 over x squared. Perfect. Perfect. Sounding familiar so far? I see some nodding. Good. All right, next one. We've got power of a power. Power of a power. In other words, I'm going to take something that has an exponent, and I'm going to raise it to another exponent. Squaring a square.
Isn't it also square the number?
When I multiply like bases, I add the exponents. When I'm raising an exponential to another exponent, I multiply the exponents. So power of a power, I multiply. So in this case, if I had x squared to the third, would I get x to the fifth? No, what would I get? Yeah, x to the sixth. Good. Good. Yes, Bruno.
If the inside was actually a number, would that be power? Like,
So if we had 2 squared to the third, that would become 2 to the sixth. It doesn't multiply the base. It just changes the exponent. Yeah. Good question. Okay. And then we have power of a product. Which means I'm taking a product, which is multiplication, and I'm raising it to an exponent. So a times b raised to an exponent. Any guesses what I'm going to do with that exponent? Yeah, it's just going to distribute through that multiplication problem. So a to the m times b to the m. Yeah. That sounds like you're playing a game and not doing math. Frowny face. Next one's a similar idea. Power of a quotient. Quotient means division. So I'm taking a division problem or a fraction, raising it to a power. What am I doing with the exponent? Distributing, thank you. Brandy's awake today. Same as a product, just distribute it through. I have a question for you. Because we've seen things that look like this, but they weren't multiplication. They were addition. Can I use that rule to do this? Bruno says no. Some of you are squinting at it like it has offended you personally. When I multiply binomials, what should I do? Got 2 options for multiplying binomials. FOIL, good, or some of you don't like FOIL. What else do you? Box method. Yeah, good. So if I were to FOIL this out, x plus 3, x plus 3, first times first is x squared. Outer is 3 times x. Inner is 3 times x. Last is 9. And you'll notice that this method missed those cross terms, first times last. So just because it works for multiplication does not mean it works for addition. So do not do this. Okay. Oh. What else am I missing? Zero exponent. There we go. Two more. Anything to the 0th power is not 0. 1. Check on your calculator. 2 to the 0 is 1. 5 to the 0 is 1. A million to the 0 is 1. But we're not multiplying 0. Remember that 0 tells me how many times I'm multiplying it by itself. So how many times am I multiplying a by itself? 0 times, meaning there's just one a. One time. It should not be itself. What you're seeing is a definition. Mathematicians have defined a to the 0 as 1. A to the 1 is a. A to the 2 is a times a. Yeah, and this is, remember when we did polynomials, this was our constant term. It was a constant times a to the 0, which didn't show up. It's just 1. So anything to the 0 is 1. And then the very last one, we've looked at negative exponents. We need to look at fractional exponents. What happens when my exponents are fractions? And when you see a fraction in the exponent, that stands for a root. So I will start with an example first. If I have x to the 1/2, 1/2 means square root. 1/3 means what? Cube root, yeah. This number that we don't usually write for square that you see out in front is called the index of the root. You'll notice that the index of the root matches the number in the bottom of the fraction. That's true over here for our general rule. So I know that this is going to equal the nth root of a. What happens to the numerator of that exponent? It stays with the base. So the bottom of the fraction becomes the index of the root. The top of the fraction stays with the base. Yeah. Three to the 4/3, 3 to the 4/3. I'm going to rewrite that in radical notation. Yes, Bruno.
It would be a 3 on the outside and 4 on the inside.
A 3 on the outside and a 4 on the inside. Can I get a thumbs up if we agree? Yeah. Very good. Very good. Perfect. Perfect. Let's do some examples that involve using these rules to simplify exponential equations and functions, because that ultimately is our goal. We want to be able to work with exponential functions. Oh. So I have the exponential function 96,000 times 3 to the t plus 2. You may be thinking, what can I do with that? So we have seen this before. A to the m times a to the n equals a to the m plus n. I want to go backwards. The question is, what is that going to look like? So the 9600 is just going to come along for the ride. When I separate this exponential, 3 to the t plus 2, what am I going to get? Yeah. 3 to the t times 3 to the 2. Multiplying like bases, add the exponents. And I can go in reverse. If I'm adding the exponents, I can split it into 2 exponentials. Yeah. 3 is the base. 3 is the base being raised to an exponent. Yeah. To separate it from the initial value that's not being raised to a power. It's just for clean notation. One of those 2 exponentials is a number that I can evaluate. What is 3 squared? 9. So this is 9600 times 3 to the t times 9. Now I'm just going to do the multiplication. What is 9600 times 9? $8,400. Thank you, Gerardo. Right? Yeah. We've taken an exponential that was being shifted to the left by 2, and we've changed it to an exponential that's centered where we expect it to be centered, but now it has a bigger initial value, which makes sense because shifting it back 2 would shift that intercept. Yeah. Good. Good. Let's try another one. G of t equals 24 times 0.95 to the 2t power. Ooh. That is 2t, which means 2 times t. That's another one we've seen. Yeah, very good, Gerardo. Power of a power, but now we want to take it and go in reverse. I want to take that 2t and do something squared to the t. So I'm going to rewrite it this way. That's a good question. Everything that's in here is a number. I can plug that in a calculator. What's 0.95 squared? That's okay. I happen to know it because I did it earlier today. It's no longer a shifted exponential or a stretched exponential. It is just a straight exponential with a starting value of 24. So simplifying the exponent on an exponential removes that issue of having to deal with those translations or those vertical stretches and compresses. We just change the base. Move all the constants out in front. Yeah. That's going to be helpful because next week we're going to learn how to solve exponential equations. And the goal of solving an exponential equation is to find the value of the exponent that makes the statement true. And we know when we're solving for a variable or isolating a variable, I want to get it by itself. So getting all of those constants out from around the exponent is going to help us solve. Yes, you may. All right. Questions on exponent rules before we move on to logarithm rules? No? Everybody still awake? Holy shnikes. You guys had lunch not too long ago. All right, so let's go ahead and move on to logarithms. Logarithms are nice. They have fewer rules. What, huh? This is the same notes. We're just going to move on to logs, right? Because the note said exponents and logs. Moving on to the log portion. First logarithm rule is the product rule. And for logs, the product rule says that if I have a product of two things inside of a log, it's going to become addition of two separate logs. Oh, let me choose a different letter there. That wasn't the best choice. Sorry. Mr. J wasn't thinking. You will notice that this goes in the opposite direction of what we would expect. It's a little weird, but it is following that same pattern that we saw with exponents. If I had a to the n times c to the n, I would get a to the m plus n. Multiplication inside a log is becoming addition outside. The reason this is mimicking those exponent rules is logarithms pick off exponents. Logs undo exponentials. So the rules for log are going to mirror what we were doing with the exponents for exponentials. When I was multiplying exponentials, I added their exponents. So when I'm multiplying inside a log, I am just adding the logs. The next rule follows that pattern. It's our quotient rule. If multiplication becomes addition, what do we think division is going to become? Subtraction. Good. And just like with exponents, it's top minus bottom. Bless you. So log of A minus log of C. That's okay. We're going to practice. Practice today, practice next week. Practice, practice. One more, because there's only 3. Yeah, a lot less than exponents. Next one is the power rule. So if I have log of a to the m, you have a power inside a log. And we're going to think back to what we did with exponents. When I had a power of a power, What did I do with the exponents? Power of a power. Multiply. Yeah, this m is going to be pulled out in front, and I'm going to times it. Logs pick off exponents. So exponents inside a log become constants in front of the log. That's what logs do. Logs undo exponentials. They pick the exponents off. Okay, so we're going to practice a couple examples using these rules to help us expand expressions, write them in long form, and take long form expressions and squish them together into a single log. Yeah? So we'll do our expand first. Log base 4 of 7x times 2y. So first off, which of the three exponent or logarithm rules am I going to use? Did I just hear product? Yeah, I agree. I see a whole bunch of multiplication in there. Before I use the product rule, I'm going to simplify the inside of that log because I see something I can do to make the inside of that log, its argument, prettier. What's 7 times 2? 14. This is actually just 14 times x times y. Meaning when I split my log, I am splitting it into 3 expressions. Log of 14 plus log of x plus log of y. And you may be asking yourself, why on earth would I want to do that, Mr. J? This is boring and tedious. Why would I do that? The answer is if I am trying to solve the equation log base 4 of 7x times 2y equals 0, I want to know where the zeros of that expression are. I need to solve, right? I need to isolate one variable in terms of the other. Doing this separates the x and the y, meaning now I can move log base 4 of y to the other side and start getting y by itself and not worrying about the x and the 14. So if I am trying to solve a log equation for one variable, this expanding process allows me to isolate the variable from all the noise. Yeah? Let's try another one. Have we seen ln before? I see shaking head no. So let's talk about what ln is before we try and simplify that. So we know all logarithms have a base, just like exponentials have a base. There are 2 buttons on your calculator that don't have a base on them. One of them is the ln button. One of them is the log button. Those logs do have bases. We just don't write them because they show up so often. We came up with some shorthand. ln stands for natural log. And it is called the natural log because it is log base e, where e is the natural base, which is a constant, 2 point something, 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 something. And you will notice on your calculator, if you have your calculator handy, that above the ln button is e with a little caret, e to the power, because ln and e are tied together. ln is log base e. When you see log, log, with no base specified, we are assuming that it is log base what? 10. Very good. We work in a base 10 decimal system. We don't write the base, we assume it's log base 10. After we finish some more examples, we're going to introduce the change of base formula. Because ultimately, if I'm doing calculations with logs on my calculator, I have buttons for ln and log. I don't have buttons for log base 4. So ultimately, we're going to learn how to change bases into one of these two because they're the easiest to deal with. But for now, we know it's a log. It follows the log rules. So looking at that expression, what do you see I can do? What do we see inside that logarithm? I see a quotient. Yeah, we know quotient means subtraction. So ln of 1 minus ln of 4 to the x. There's one more thing I can simplify. Jordan, do you see it? No, Jordan doesn't see it. Raise your hand if you see it. One more thing I can simplify. Gabe, do you see it? The x. Yeah. If I have an exponent inside the log, it comes out in front. Logs pick off exponents, slap them down in front. That is helpful. Oops, that should be minus and not equals. I've now taken an expression that was logarithm of a fraction, and I've turned it into an expression that is linear. Log of 1 is a number. Log of 4 is a number. This is a number minus x times a number. That's slope-intercept form. So it started looking like scary exponential. It's actually nice, pretty linear. Yeah. Good. All right, let's try going backwards. If you are asked to condense a logarithmic expression, it wants you to take all the separate logs, squish them down into one. What rule am I using here? Dayanara, what rule am I using here? There's only 3 for logs. Which log rule? Product. Very good. Addition outside becomes a product inside. Yeah. So this is going to become one big natural log of 7 times x times y. Happy face. Okay, let's try another one. Wait, what? Last one got 2. This one is on 2. I give you as many examples as I want because I'm in charge. So log base 2 of 28 minus log base 2 of 7. Jackie, what log rule am I going to use? There's only 3. Product, quotient, power. Quotient. Good. This looks like the answer to a quotient rule problem. I know subtraction outside the log becomes division inside the log. And it's top minus bottom. So 28 must have been the top of the fraction. 7 must have been the bottom. What is 28 divided by 7? Yeah? And that, on your calculator, is a nice pretty whole number. Good. One more. Because it's good for you. So 4 times log 7 of C plus 1/3 log base 7 of A plus 1/3 log base 7 of C. Well, that should be B. I'm sorry. B. Ah. There we go. A couple rules here. I want to start with the power rule. What did those coefficients start their life as? Exponents, yeah. Logarithms take exponents and turn them into constants out in front. So this started its life as log base 7 of C to the 4th. I agree. The next one must have started its life as log base 7 of A to the 1/3 and log base 7 of B to the 1/3. It's okay, we're going to condense it in just a second, and then there'll be less log base 7s. I'm adding the logs, and they all have the same base. So if I squish them into a single log, what am I turning that addition into? Multiplication. Addition and multiplication connect. Good. So this is going to become log base 7 of C to the 4th times A to the 1/3 times B to the 1/3. And if you got that happy as a math teacher, I'd be pretty happy. But we are in pre-cal now. We could push a little bit further. I see some simplification that I can do inside the log. Suggestions. What can I do to make the inside of that log prettier? Exponents. Yeah. What am I going to do with those exponents? Am I allowed to do that? I see some nodding, yeah. That was the power of a product rule. We're undoing that distribution of the exponent, yeah. One more thing. Fractional exponents. What do those represent? Ooh. Roots, yeah. This is a cube root of A times B. Log base 7 of C to the 4, cube root of A times B. Yeah. Happy face. Really quick, want to do change of base before I set you loose. Before we do that, questions on the log rules? No. Okay. So hopefully you all have your calculators out, because the next thing I'm going to show you is to make your life easier calculating logs. And that is the change of base formula. So change of base formula, log base b of x. And I want to rewrite it in a base that my calculator has a button for, meaning a log or a natural log. I do new log on top. I'm going to write log base n for log base new. Yeah. And then for the arguments of the new log, in the numerator goes the argument of the old log. And then in the bottom goes the base of the old log. Argument on top, old base on bottom. We're going to do some examples because that looks really weird on paper, but it's quick and efficient on a calculator. So let's say I want to evaluate log base 3 of 22. I don't have a base 3 button on my calculator. So I'm going to use change of base to turn it into a button I do have on my calculator. Do we want to do base 10 or base E? Preference, Alan? 10. So log base 10, parentheses, parentheses. And then I need to figure out which of those old numbers goes where. I've got a 3 and a 22. Which one of those goes in the numerator? The 22. Very good. Argument of the old log on top, base of the old log on bottom. You're going to grab your calculator and evaluate that for me. I'm going to do it too. Make sure you close the parentheses of the log on top before you hit the division button. When I did that, I got 2.81, and it said 3.5, which I'm going to round to 4. And I see some nodding. Good. Thank you, Lucera. Ooh, and I made a spelling error, and nobody called me on it. You guys know I can't spell. You got to let me know when I do that. All right, one more. It's good for you. Log base 6 of 5.38. You what? Huh? You can. You go math and you go into a submenu, and there is a way to do it. But oftentimes, if you're doing rapid log calculations, once you've got change of base formula down, it's faster to do change of base than to go into the submenu of your calculator. And as math nerds, we're shooting for speed. I'm going to do ln this time. I'm going to use natural log. ln, because I was a physicist at one point, and we used natural log a lot. Pattern's the same. Argument of the old log on top. Base of the old log on bottom. So natural log of 5.38 divided by natural log of 6. And I got 0.939. One something something something. You see a whole table of nodding heads. That's a good sign. Good. Good. On your homework, there is some delta math to practice with exponent and log rules. It's pretty short. Please do it this weekend so that if you run into sticking points, you can ask me on Monday. On Monday, we're going to do a little bit of review with these rules, and then we're going to start talking about how to solve equations using those rules.